Good morning, everyone. Today, I wanted to give you guys a more intuitive way of understanding why it is that when two complex numbers multiply together, that the resultant vector, why it is that when two complex numbers multiply together, say a z and w, that the resultant complex number has the sum of the angles. So we have arcz plus arcw. Why is it that this resultant, you add the angles of the components? Why is that? So generally the way that this is kind of explained is that it's through a rigorous trigonometric expansion, and you can see that it does indeed collapse into cos theta plus phi, right? But I never found that very intuitive, so I'm going to give you a more geometrically intuitive way to understand that. So let's say that we have these two vectors, z and w. Let's let z equal x plus I, y. And let's let w equal a plus I, b. So let's really have a look at what's going on when we multiply z and w. So z w is equal to, I'm going to leave z there, right? And what I'm going to do is I'm going to substitute this Cartesian form of w into the multiplication. So a plus ib, right? And now let's expand this. So I'm going to have z a plus I z b. Now that might not look very exciting, but let's have a look at each of these components, because that's going to be quite insightful. Okay, so we have a times z and b times z. Now what is a times z? A times z is nothing but z scaled up or down by a factor of a. Generally, if a is bigger than if a is bigger than 1, which it generally is, then it's going to be a longer vector. It's going to be scaled up. And bz, similarly, is going to be a scaled up version of z as well. And we're going to be adding that onto z of a. So let's have a look here. What's this going to look like? So if I draw out another plane, and I have real, imaginary. So if I have z, so say that's my trusty vector z. Obviously this is arcz, right? Right, z. What I'm going to do is I'm going to scale this up by a factor of a. So I'm going to make it bigger by a factor of a. So I'm doing this in blue if you can't see. Okay, so this whole length is scaled by to a factor of a. Now, I'm going to also add on bz, right? So that would represent the kind of length of bz, but that's not quite it. It's I bz. so I'm going to have to multiply zb. So this vector here. I'm not just adding it on directly. I'm adding it on plus, but I'm also multiplying it by I, which means that I'm actually rotating this vector. I'm rotating this vector by 90 degrees. So it actually ends up over here. And the reason for that is because we know that when we multiply by I, geometrically it can be interpreted as a rotation of 90 degrees. So now we're almost done. Let us draw in the resultant complex number. So say that dotted line is my resultant. Now let's have a look at what this angle is here, right? Well, we see that this is it's a 90-degree triangle, so it makes it nice and easy for us. And we know that this length is scaled by a factor of b. So this is AZ, so that's BZ, and this is AZ, right? Now, let's take the, so this will also be BZ. So let's take the tan here. So let's say that this angle will be tan inverse of what? BZ on top of AZ. Now the Z's cancel out and we get tan inverse of B on A. Now what is tan inverse of B on A? Well, tan inverse of B on A is simply arg W, isn't it? So we have arg W here. And now I'm hoping that you can see already how it might be that the resultant complex number has, the argument of the resultant complex number is the summation of the arguments. So this dotted line is the resultant complex number. And what we see is that we do indeed add together arg Z plus arg W. So I hope that was an intuitive way of seeing how it is that this resultant vector, the angle, is indeed composed of arg Z plus arg W, as you can clearly see in this diagram. So I hope this video helped, and I hope to see you guys again next time. Thank you.